Thank you. This is the sixth and last of this season's Royal Institution Christmas lectures on planets. And today our topic is planetary systems beyond the sun, beyond the one that we live in. We have in previous lectures talked about most of the other planets in the solar system, certainly from Mercury to Saturn. We've said a little about Uranus, almost nothing about Neptune and Pluto. And we've touched on asteroids and comets. Now, all of these objects, except for the comets, are in a kind of flat plane, which is also the plane that the sun rotates in. And that system is called the solar system. And it's a lovely system, a star in the middle and the planets strung out like beads on a string. And we note that there are other smaller systems that look a little bit like that. The moons of Jupiter, for example, are similarly strung out in the equatorial plane of Jupiter. Likewise, the moons of Saturn. Likewise, the moons of Uranus. It looks a little bit as if whatever process it was that made the solar system made some miniature solar systems as well, back 4.5 or 5 billion years ago when the solar system was formed. And the general idea, which is mostly accepted by astronomers on how planetary systems form, is that there are great gas and dust clouds in interstellar space, and that here and there are condensations, places where there are more matter, more gravity, material collapses while rotating, and big lumps become so hot during this collapse that they have thermonuclear reactions which convert hydrogen to helium, release energy, and that lump turns on and becomes a star. Smaller lumps formed at the same time, but not as massive, don't have high enough temperatures for thermonuclear ignition, do not shine by their own light, are dark objects shining by reflected starlight, and those are called planets. Now, if that's what it's about, there ought to be lots of planetary systems. Planetary systems would then clearly be connected with stars, and so let's just spend a moment talking about the life cycle of stars. Stars are born, they live, they die, and there are an awful lot of them, as this picture reminds us. Here is a photograph of a naked eye object, the Orion Nebula. It is the middle star in the sword that's hanging from the belt of Orion, who's a hunter, and in that psychological protective test. But this is the Orion Nebula, which is a kind of stellar nursery, a place where stars are forming recently in the last millions or tens of millions of years. And for all we know, planets are forming rapidly here as well. Stars live for a sizable period of time. Our sun has a lifetime in its present stable state of about 10 billion years, and then they die. Here is the product of the old age of a star more massive than the sun, a great nebula, a star which has blown its top, blown its outer atmosphere out, and we see the remains of that outer atmosphere surrounding the star, which is in the middle of this nebula. And there are even more colossal explosions. This one is called the Crab Nebula, and it is a star which blew itself up in a titanic explosion, which would surely have vaporized any planets that were around it at the time. Now, the sun will not go through such titanic explosions. The sun will, some 5 or 8 billion years from now, gradually grow, become an immense, distended, cool red star called a red giant. It'll become so large that it will engulf the planets Mercury and Venus, and possibly even the Earth. But even if the Earth does not wind up inside the sun, there will be so much sun in the sky that the oceans will boil, the atmosphere will run away to space, and the Earth will be slightly more unpleasant than it is today. However, since that is going to happen 5 or 8 billion years in the future, it is not our most pressing problem. And for all we know, human beings or our remote descendants will be equal to the challenges of that time. After that, the sun will slowly contract and become a hot, dense, white object called a white dwarf, which will gradually decay, cool, and become a cold black object in space. There are many red giants and white dwarfs in the sky, and here is an artist's conception of a planet in foreground which is circling a double star, a red giant and white dwarf which go around each other, and the planet going around both of them. Each object casts 2 shadows, one white or anti-white, one anti-red, and that's a kind of different place. You would immediately know you were somewhere else if you found yourself miraculously transported to that planet. And here is another artist's view of a red giant, white dwarf double star. There are lots of them. In fact, most of the stars in the sky are members of double or multiple star systems. So a single star like the sun is a rarity, an anomaly. And occasionally there are double stars which are so close that they touch, and star stuff flows between them and around them. They're called contact binaries, and there are a lot of them. Now, in the immediate neighborhood of the sun, there are lots of stars, and most of them are double or multiple stars, and there are a lot of red giants and white dwarfs among them, but more stars like the sun. And I'd like to do a brief pointing out of the stars in the neighborhood of the sun. We've made a model here which shows by no means all of the stars near the sun, but at least some of them. We'll need the overhead lights down to really take a good look at this. And so that we will have no trouble identifying the sun, we've made a lot of spikes on it. It's this funny-looking object. The sun doesn't really look like that, but that's just so we won't lose our way in interstellar space. The nearest star system to the sun, which is here, is a triple star system right here. 2 biggish stars and 1 small one. This system together is called Alpha Centauri. And the little one, which circles the 2 big ones, is sometimes called Proxima Centauri, Proxima for near, because at certain points in its orbit, it is the nearest star to the sun. This triple system of Alpha Centauri, which you can see in the southern hemisphere, is about 4.5 light years from the sun. The nearest single star to the sun is this little fellow right here. This one, I'm going to touch it and make it move. There he goes. That wobbly one is Barnard's star, and as I'll show you in a moment, it is wobbly in more ways than one. Over here is Sirius, the brightest star in the sky, and over here is Tau Ceti, which is the nearest star that is more or less like the sun, and that's a single star. And we talked about Tau Ceti in the first lecture when I tried to imagine a constellation of the unicorn in somebody else's sky. And that's how far we had to go, almost 12 light years from the sun, in order to have the configuration, the perspective of the stars change a little. Well, the typical distances between the stars are several light years. And the galaxy, the Milky Way galaxy, is much wider across than that. It's roughly 100,000 light years in diameter. Now, suppose there are planets around the nearby stars, as we might well expect. How could we detect them? You can't just look out and see a planet because the planet's small, dim, hidden by the bright light of the star nearby. You have to do something special. Now, there are several kinds of special things that we could do. One thing that might happen is this. We might have a device at a telescope which measures accurately the amount of light coming from a star. Suppose this is the star. Suppose the planet were to pass in front of the star. We couldn't see that just by looking at the star, but the starlight is dimmed a little bit when that happens. So if we connected our photocell to some ammeter, like the one we've used before, then when something passes in the way, the current goes down. And this now is a very big planet, which is passing very close to the star, so there's a big deflection of our needle. In a more likely case, there is a very small planet, which is a much bigger distance from the star, and so it will be just a tiny deflection. It requires very sensitive measurements, but it certainly can be done, and this is a kind of way of searching for planets around other stars, which is just beginning to be done. Now, we can think of a second way. I'm going to mention 3 ways. There are, in fact, more, but I just want to give you a sense of how it can be done. A second way is this. The planet, after all, shines by reflected starlight, but because it's so close to the star from our point of view, it is swamped by the bright light of the star. If we could somehow shield our eyes from the star, we might be able to see the reflected light from the planet. That's called occulting, or hiding the star. So over here we have a planet which is not shining by itself next to a bright light which will represent a star, which is shining brightly. There'll probably be several people who will have to squint as a result of this. And so here we can see that the star is clearly visible, but no trace of the planet because it is swamped in the light of the star. Now, as Mr. Coates slides an occulting object in front of the star, we see the planet sitting there revealed for the first time. And now if we take the occulting device away, we can't see the planet again at all. Thank you, Bill. Now, how can we actually do this in a real situation? Well, the best way is to use a steady, large, sharp edge that's already in space to hide the star and, if we're lucky, reveal the planet. And there is such an object. It's called the moon. And if we could get in the right angle, so the moon could just barely blot out the light from a star, we might then, if we had a sensitive detection device, see the light of the planet, which goes around that star. This requires space vehicles to get at the right position so that the edge or limb of the moon occults appropriate stars. And that is a second technique which is about to be exploited in the next decade. There is a third technique which has already been put to use. And it doesn't actually involve a trolley, but we have a trolley here for a reason. And I will shortly need a trolley assistant, but not yet. And let me say how this works. This yellow sphere is, of course, intended to be a star. And this black sphere is intended to be a planet. You can see the star, but not the planet. The two go around a common center of mass. So in space, they move like that. And imagine that we're lucky and that they are at this angle to our line of sight. Now, you can't see the black planet, but you can see the yellow star. And so the yellow star is doing a kind of bobbing motion. But stars also move with respect to other stars. And now I need someone to help me pull. Yes, right here. Now, this is very easy. The only trouble is that the string tends to come off. Now, if you would slowly pull this while I tend to, good, that's good, you will see that the star tends to make either a spiral or a sine wave in space. Thank you very much. Now, could you just push it back here? Thank you. You have just moved a sun. There are very few people who get to do that. Thank you very much. Now, that kind of motion, to really pick it up, you have to see a few revolutions of the planet around the star. Jupiter takes 11 years to go around the sun. So you have to be very patient and make very precise motions, very precise measurements. Well, that has been done for Barnard's star. And while there is still some debate on the data, there are two groups who have worked on this data, and each group seems to find such a motion, although the two groups don't see the same kind of motion, so they're still arguing with each other. And if that is the case, they have found one or more planets around Barnard's star, which, let me remind you again, is this tiny little star called an M dwarf. We sort of feel sorry for it just because of the name. But around it, if these results are right, are one or two planets of Jovian mass, like Jupiter. And if that's true, it is a most important discovery because it's the nearest planet where we have a chance of finding such a thing, because a planet going around more than one star would have a very complicated motion, and it would be less easy to find out what it's about. Now, we will, I believe, in the next decade or two, have made a very serious and thorough search for planets around nearby stars, sufficient to tell whether they're there or not. If, as we think they are there, we will have then extended the Copernican perspective and discovered that planets are a frequent, if not invariable, accompaniment of stars. If we find no or few planets there, it will say that, to our surprise, there's something special or unusual about planetary systems in space, and that's also, of course, important to know. Now, there's another approach to this problem, and that's theoretical. We can put in the kind of physics that we think is important for planetary systems forming out of a gas and dust cloud, and let the computer make all kinds of parts collide and see what happens at the end. So let me show you in a moment the result of a computer program which we've used at Cornell University, which does just this. It imagines a big dust cloud in which there are tiny little lumps of matter which go through the dust. And every time they collide with a dust particle sticks. When the growing mass becomes big enough, its gravity attracts gas. When two of these growing planets collide, they stick, and the whole process is continued till all the gas and dust is used up. What are the results? Well, the next picture shows our solar system in a way which will be useful to understand the computer results. And we have the various planets laid out for us, from Mercury here, Venus, the Earth, Mars, the biggest asteroid. Those are the terrestrial planets, and you can see they're little guys, and they're in close, around 1 astronomical unit. An astronomical unit is the distance of the Earth from the Sun. Then there comes Jupiter, Saturn, Uranus, Neptune. These are planets that have been shaded. They are bigger than the terrestrial planets. They're the gas giants. And you can see they're out at roughly 10 astronomical units. Well, that's the kind of system we have here. What does the computer make? Well, under some circumstances, the computer makes systems like this. And you can see it's almost identical. Terrestrial planets in close at around 1 astronomical unit. Jovian planets further out at around 10 astronomical units. These are cousins of our solar system. They're very similar. And while the computer requires certain starting conditions to wind up with planets like our own, the fact that with such simple physics you can wind up with such planetary systems is encouraging. Now, if the gas and dust cloud is very thin, if there's not much matter around, then we don't form big planets. We form something like a string of asteroids all the way out. Or if there's a lot of gas and dust, we might form a system in which there's Jovian planets close in and terrestrial planets far out. That's very different from what we have here. This is a reminder sort of system we have here. And we might even have a system, if we had a lot of gas and dust to begin with, in which planets of such large mass are produced that they are stars. So the computer also makes double or multiple star systems in the appropriate cases. Now, if it is true, and we don't yet know it is true, but it's beginning to look as if it's true, that planets are a dime a dozen. No, you don't have a dime. A sixpence a dozen. We have previously found that the steps necessary for the origin of life seem to be very easy, requires only the most common cosmic conditions. We know that for evolution we need time, but we have a lot of time. There are stars which are twice as old as the sun. We know that the development of intelligence, the evolution of our kind of thinking on the Earth, has taken a long time to come into being, but it has come into being only halfway through the history of the sun. And other things being equal, it is probably better to be smart than to be stupid. And smart means being able to deal with the environment. Since we know that the laws of nature are by and large the same throughout the universe, then beings that evolve everywhere must be funneled in some kind of intellectual sense so that they think about the universe more or less in the same way. There will be limitations, of course, but to some extent this should happen. This kind of thinking suggests that not only might there be life on other planets, countless other planets, but also intelligent life, beings as wise as we, as artistic, as ethical, as technological, interested as much as we in novels or music, and perhaps lots of other things as well. There should be many that are more backward than we, but because of the immense vistas of cosmic time, there should be many much more advanced than we. And if that's the case, it would be nice to say hello to those fellows. They should not look like us. They will have evolved differently on a different planet, and we know that evolution has a strong random or stochastic component to it, but they may think enough like us to be able to make contact. Well, there are various ways of doing this. A very slow and not fully serious way is to put a message on a spacecraft which will wind up in interstellar space. It's a little bit like throwing a bottle into the cosmic ocean. The chance of it being picked up is small, but it is at least psychologically good for the stranded dweller on the desert island. He's making some effort to contact the cosmos. The first attempt to do that was on a spacecraft called Pioneer 10 and 11, and this is a plaque affixed to the exterior of that spacecraft. And let me just very briefly say what this is about. This will be very brief. This says, here's our unit of time and space in terms of the hydrogen atom. And down here it says, here's our solar system, sun and lots of planets strung out. The spacecraft was launched from the third planet, passed by the fourth, came close to the fifth, and then went into interstellar space, and there it is. Over here is a map of the positions and periods of regularly pulsing cosmic radio objects called pulsars. And this part of the message says a little bit about when and where we are. And then over here at the right is the most obscure and mysterious part of the message, a man and a woman. They, of course, are apparent to us, but only because we happen to live here. It's very unlikely that there are human beings anywhere else, and so if there are any recipients of this message, they will wonder very much what this is. Are they holding it right side up? It will not at all be obvious that these are the creatures that launched the spacecraft. Because space is so empty, Pioneer 10 and 11 and Voyager will never enter any other planetary system, and so we do not know that anyone will ever pick it up, and in fact, it seems unlikely. But one of the major reasons why we send such messages is not just to contact intelligence out there, but also to contact intelligence back here, to raise the cosmic consciousness of human beings. And here is an indication that, at least on Earth, the Pioneer 10 greeting was received with some degree of friendliness. This is a billboard in Pasadena, California. Now, a more elaborate attempt to communicate, but along the same lines, was on the Voyager spacecraft, as I mentioned before. And what we'd like to do now is to play an edited portion of a small part of the Voyager phonograph record. Phonograph record, you may remember, has greetings in many languages of human beings and also of whales to the cosmos. It has 116 photographs on the record in audio form about what the Earth is like. It has an hour and a half of the world's music, and it also has an elegant sound essay of the sounds of the Earth devised by Anne Drian of the United States. And we'd like to play a little bit of that greeting to the cosmos. And I think I would like maybe two people to come up here and listen to it with me. I think I'll go around the front if I can. And what I'd like you to do is to give me your impression of what the sounds are. You will have some bias because you will be human beings having grown up on the Earth, and you will know sounds better than extraterrestrials. But still, it'll be interesting to see how well you can do. Oh, I see so many eager faces. I don't know who to choose. Can I pick you right here in the jacket? And you right there in the red sweater with the pullover, please. And let's start the Voyager Sounds of Earth record. And maybe I can just ask you to tell me what it sounds like.
Lorry.
A lorry. Let's listen to it.
Water bubbling.
Water bubbling. Boiling water. Explosion.
Fish.
A house falling down.
A submarine.
A submarine. This isn't what we intended at all. And if humans can't get it, extraterrestrials never will.
Jungle.
Jungle, good, we agree on that. Who's that? Well, we certainly have the sense of some kind of life there. What's that? Chimpanzee is the suggestion. Baboons, we're certainly into primates, into monkeys and apes. Remember, this is the Earth talking to the cosmos. Okay, now it gets quiet. Chimpanzee, it's proposed. Now the wind starts up, and someone is crying. Who's that? A wolf, wild dog. That's good. Hyena, good. Now there's a background noise. What's that? A heartbeat. The first human. Now what do we do?
Someone up here on the door.
It's a dog. So we had a wild dog before, and now a domesticated dog. Have any idea what this is?
Bicycle path.
No, that was actually an anvil. The first making of metal.
Morse code, very good.
Siren. Ship's horn.
Ship's horn, foghorn. Some machinery, it's true, but what? It was a horse-drawn carriage. Train? A new car or an old car? Old one. You think that was a crash of the car? That was a jet airplane.
Rocket starting.
Yes. Yes, the man said we have liftoff. Can you guess what that is? Well, that's the end of this edited part of the Sounds of Earth. I'd like to thank both of you for your help. I would say that about half of what we hoped the extraterrestrials to figure out, you figured out, which in a way is disappointing to us because you people have a big head start being from the planet Earth. But on the other hand, you've just given your very first impressions. And if anyone did find this in space, they would be giving very close scrutiny. They would work on it for many days, weeks, and months. Thanks very much for trying to interpret a signal from an exotic and distant planet. In fact, the general idea of that Sounds of Earth wasn't perfectly done throughout, was the evolution of the Earth. So we started out before life with volcanoes and earthquakes and rain, and then the evolution of life, and then up the evolutionary tree, and then human beings coming in, and then technology, then rocket to interplanetary and eventually interstellar space. And then the last sequence was a kiss, very important, a baby crying, a heartbeat and other vital signs of a human being. And then the last sound was the sound of a pulsar, a cosmic object which regularly sends out a signal and is in some sense indistinguishable from the beating of a human heart, a sense of tying up of human beings and the cosmos. Now, these are fun. They are not extremely rigorous ways of communicating with the cosmos. One point which we might remember is that it's probably not up to us to send signals out to those other fellows, since we have just achieved the technology to do this. It's much more likely those other fellows are sending signals to us, messages to us. Now, what's the way to do that? Spacecraft travel very slowly. Light travels, radio travels very fast. Do you remember this?
Hello, universe.
That was, I don't know if the person who said that is still here, but that was said at the first lecture. And maybe you remember that there was a signal from the Earth, which we imagined going out at the speed of light. By the end of the first lecture, it had passed the orbit of Jupiter. And by now, that signal has gone about 1,000 astronomical units. An astronomical unit is the distance between the Earth and the Sun, 150 million kilometers. It's gone an immense distance, far beyond Pluto, out to the realm of the comets. It would take a typical interplanetary spacecraft about 1,000 years to go that distance. And radio has done it in just a few days between the first and sixth such lecture. Radio is the way to communicate. It's fast, it's cheap, you can send an enormous amount of information on it, and we already have large radio telescopes on the Earth which are capable of communicating over immense distances. This one, chosen because we are in Great Britain, is the Jodrell Bank radio telescope, 250 feet across. It turns in azimuth and in altitude and points to different parts of the sky to see what's coming from that place in the sky. It has never, to the best of my knowledge, been used to see if there are signals from intelligent beings elsewhere being sent our way, but it could be so used. Notice the scale. It's a very large object, and there are little stairways here, for example, which are the size of a human being, and this thing's so much larger. The largest radio radar telescope on the planet Earth is the Arecibo Observatory in Puerto Rico, which we saw once before. And here it is now. It's 1,000 feet across, and it is extremely powerful in its ability to send and receive such messages. Suppose there were some other civilization on a planet of some other star which had an Arecibo. So we're not imagining that those fellows are much more advanced than we. And we use our Arecibo. The two are moved further and further apart. How far apart are they when they can just barely communicate with each other? The answer is they are many thousands of light years apart. A light year is 6 trillion miles. So we have at the present time the technological capability to communicate over immense interstellar distances if only we were to choose to do that. There are questions, for example, of what frequency or station to tune to. And this slide is just to indicate that this is the vertical axis here shows the temperature, the amount of noise in space. And here we have different frequencies or stations that we could tune to. And we see there is a place where there is a minimum of noise. That's the place to listen to. And it turns out that many molecules, hydrogen, for example, or formaldehyde, like to give off radiation in that noise minimum. So by luck, there are some natural frequencies at just the place where the noise is a minimum. And so by sending signals, some other civilization might communicate an enormous amount of data to us. Here we have a radio telescope sending information, there's a symbolic picture, information on a complex organic molecule, in this case DNA, to the stars. We might receive such a message if we used our radio telescopes properly. It might be an extremely rich amount of information. With our existing technology, we could send the Encyclopedia Britannica to a nearby star by radio in just about a week. And wouldn't it be lovely to get someone else's Encyclopedia Galactica and see how they think about the universe? What is their society like? What do they look like? What's their organic chemistry like? What are their planets like? What do they like? What are their ethics about, their religion, their philosophy? Wouldn't it be lovely to make contact with another civilization that has arisen and evolved independently? Well, one thing you'd have to do first is to be sure you can understand the message. Why should we expect that beings that are very different, evolved in a different place, different period of time for the revolution, should be able to send us a message that we can understand? And the reason that I think that's likely is that they live in the same universe as we. They must deal with the same laws of physics and chemistry and astronomy as we. To test the idea that a signal could be understood, we did a little experiment. We can only use human beings. It's too bad. I wish we could use some other intelligent beings to make such an experiment, but we're restricted to people. They're the only ones we know about. And so what we did was to devise a complicated message, which you can see here, of zeros and ones. The 0 and 1 might be a long and a short radio beep, you know, beep, 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 beep. Or it might be 2 frequencies, beep, 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 beep. Might be many things, but it's a language of 2 letters. And you can see there's an enormous number of zeros and ones, in fact, 27,000 and something of them here. You can't tell just by looking at it, oh my goodness, I see what this is. You have to think about it. Now the key to this is that the total number of zeros and ones is 31 times 31 times 31. 31 cubed. And it suggests that it's a pictorial message in 3 dimensions. And if we were to write it in a sequence of 31 symbols, then go to the next line, then you see it starts getting a remarkable regularity. And so what we did is to give this message, not made simple in that way, to some graduate students of mine at Cornell University. They were told nothing about what was in it, how to decode it, and their job was to figure out what it said. And here they are describing the process they went through to figure out what the message was about. These are all graduate students of mine who are reasonably clever. But none of them work on this particular problem.
Well, we gathered together in the Mars room and stared at it and cursed volubly at length. Kathy noticed that 31 divided into 29,791. And it was determined that the remainder, 961, was 31 squared, which left us with a 31 by 31 by 31 sequence. And then we sat together, 6 of us, for 4 hours, transcribing zeros and ones, screaming and shouting from one office to the next, and complaining about the typographical errors until we could get the sequence, which is shown in frames there.
They were making good progress. They found some errors in the transcription of this that the BBC had made, in fact, but they figured out how to get around that.
It was not necessarily a 3-dimensional model at first. It could have been a movie, because what we see, what eventually turned out to be the corner markers of the cube and the lines which drew the pattern of the cube could have been just frame markers for a movie or a slideshow. It could have been separate frames. And it was only when we had drawn them out and looked at them that it became very uncertain whether it was anything like that.
Since it was a dull movie, you figured it was really a 3-dimensional.
That was about the size of it.
So here we have some plexiglass things. So a 1 will be represented by a black square and a 0 by a transparent square. Here's a whole sequence of transparent squares. That is, this would represent a sequence of zeros. Now, building up as the message requires, first space is a 1, which is black. Second space, another 1, which is black. Third space, other 1, which is black. And in fact, it's black 1s all the way across the top line. So the top line there is a sequence of black 1s. Next line begins with a black 1, but then there's a sequence of zeros represented by the transparent markers, and then a 1 at the end. Now we have the similar pattern building up. Black edge, transparent interior, which goes for a number of lines further. Now the next line is different. It starts out with a 1, has a sequence of zeros, and then there are 3 1s in the middle. Then the same sequence of zeros, and then a 1. So Here is the black 1 at the periphery. Then here are the zeros. Next are the 3 black 1s, and then there will be zeros and a black 1 there. And the remainder of this frame fills in like this. So we now see the picture is a black border and a kind of Maltese cross in the middle, and everything else blank. There are many other layers, and when we build them all up, we result in a pattern, which we will shortly see, and that is the answer. We can tell this is the right answer because of how regular the geometry is. We couldn't have gotten that by accident. So here is, in 3 dimensions, what the resulting model is like. Now let's see what the graduate students have to say about their interpretation of this funny-looking message.
Well, the first thing that came out of our analysis of that object was that in profile it was strongly reminiscent of Mickey Mouse. And in fact, it's still not clear whether that's the case or not. And although we know that you have a sense of humor, Mickey Mouse was not our idea of a joke, so it had to be something else.
The only thing it really looked like was a molecular orbital type drawing of a molecule. And the first one that came to my mind was formaldehyde.
And Kathy is in fact right. This was intended to be a formaldehyde molecule, although it does look a little bit like Mickey Mouse, in which there's a carbon atom, 2 hydrogens, and an oxygen. Now, what could the significance of that be? Why go to all this trouble to simply say formaldehyde? And the answer is that formaldehyde has a radio frequency attached to it. And what all of this trouble is about is the message is saying, don't listen on this station. This isn't the station that's interesting. Listen on the formaldehyde station, and that's where the Encyclopedia Galactica will be. So as soon as we get that message, quick, we turn the frequency of our radio telescope to the formaldehyde frequency, continue to look at the same star we're looking at, and then hopefully get such a message. That's the general kind of idea. Notice that if we made a serious such search and succeeded, the results would be inestimable. We will have ended the isolation of mankind from the rest of the universe forever. If we made a serious search and failed, we would have determined something of the uniqueness, fragility, preciousness of human beings. And it seems to me either way we win. And there are signs in the United States, Canada, Soviet Union, perhaps other countries, that a serious search for radio signals from civilizations on planets of other stars is about to begin. Now, one often comes upon some other ideas about extraterrestrial intelligence, namely, why go to all this trouble with radio telescopes when the extraterrestrials are already here? We sometimes hear such an idea. The ideas are often expressed in terms of unidentified flying objects and in terms of ancient astronauts. Now, there's nothing silly about being able to fly between the stars. We are already doing it, although at an extremely slow pace. It's taking us about 80,000 years to go from here to the nearest star with our present space vehicle. It's a little slow. But other civilizations more advanced than we might very well be able to do it in much shorter periods of time. So maybe we are or have been visited. It's not ridiculous. On the other hand, it's such an important contention that we should demand only the most rigorous standards of evidence. And my judgment is that on the ancient astronaut business, what happens is people look at big buildings constructed long ago and say, my goodness, I don't know how that big building was built. Probably people from somewhere else built it. Yes, maybe from Egypt, but not from some other star. These ideas often show an ignorance of archaeology. Our ancestors were smart. They could build big. There is no artifact in earlier human history, so far as I know, which requires extraterrestrial intervention. Likewise, on unidentified flying objects, there are things seen in the sky which are unidentified. That's what an unidentified flying object is. It means we don't know what it is. It doesn't mean that it's a space vehicle from somewhere else. And there ought to be things in the sky that we don't understand. The sky is very rich in phenomena, astronomical, meteorological, optical, and man-made phenomena. And therefore, only a very reliable sighting of an extremely exotic object ought to be considered in any way relevant to our problem of life elsewhere. And to the best of my knowledge, there are lots of exotic reports, but none of those exotic reports are reliable. For example, a 30-foot diameter metallic-shaped object lands in a suburban garden. A seamless door opens. There's a fascination with seamless doors in these stories. A metallic robot walks out, picks a flower, smells it, pets the cat, waves to a lady hiding behind her sliding glass door, turns on his heel, still smelling the flower, enters the UFO, the seamless door closes, and it takes off into space. Now that I would call an exotic story. No question about it. But when we look closely into that, turns out no one in all of Long Island, New York City, besides the one lady, noticed that this had happened. And the cat was unavailable for corroboratory evidence. And that's an example of an exotic story that isn't reliable. On the other hand, there are reliable stories. 200 people see something, but they're not exotic. It's a light in the sky. There are no cases where 200 people see something as exotic as what I just said. No cases where there's a piece of the spacecraft that someone captures and sneaks into a laboratory so we can investigate it. No one has ever managed to steal the captain's logbook of one of these supposed interstellar spacecraft. And until that sort of thing happens, it seems to me we must be very cautious and skeptical, because extraordinary claims require extraordinary evidence. It would save us a lot of trouble if those fellows would come here instead of us having to go out and find them. I'm not opposed to it. It's just that there isn't a smidgen of good evidence to support those ideas. I wish it were otherwise. And yet, we live in a universe which is astonishingly rich and full of objects. I keep stressing the number of stars. The number of stars that make up the Milky Way galaxy is about 250 billion. We don't have a picture of the Milky Way galaxy taken from outside because we don't know anybody who's been outside, or at least I don't. But here is a picture of the nearest galaxy, like our own. It's called M31. It's in the constellation Andromeda. If this were our galaxy, where would the sun be? Would it be here in the middle where it's a central or at least well lit? That's not where we'd be. We'd be out here in the galactic suburbs in some rural place where there's almost no stars. Not a very important, significant place. And there are many galaxies. In fact, there's not just one here. There are 2 satellite galaxies of M31. But there are at least billions of other galaxies. Here is a photograph in which there are more galaxies beyond the Milky Way than there are stars within the Milky Way. This is a galaxy. That's a galaxy. That's one. That's one. That's one. That's one. That's one. There may be 100 billion other galaxies, more or less like our own. If that's the case, there are something like 10,000 billion stars in the accessible universe. Is it likely that our sun is the only one of those stars which has an inhabited planet? I think that that's unlikely. Now, the time we live in is a very epochal one. It is a time of great transitions. This is the first time in human history that we, or at least our instruments, are leaving the Earth, are going into space. And we're doing this with small, unmanned space vehicles, very largely. And here are some small, unmanned space vehicles coming down from the top of the Royal Institution. We have previously talked about the Viking lander on Mars, the Viking orbiter, typical interplanetary spacecraft the last few years. Here is the Pioneer Venus entry probe and the Pioneer Venus orbiter, missions to be launched this year and next. Pioneer 10 and 11, which had that little plaque on it, right here, out beyond Jupiter on their way to Saturn. Here is Voyager. Here's Jupiter orbiter with probe. Here is a new generation of spacecraft, less noisy than we hear, being described and worked on. This is an ion drive to get to the outer solar system very fast. And this object here, looking like some great windmill in space, is a crude model of a kind of spacecraft which is under development, under study, which will be a half-mile or more across, a solar sailing ship which will use sunlight as sailing ships use wind to travel in the space between the stars. And for all I know, in the first few decades of the 21st century, there will be interplanetary regattas vesting with each other for the fastest time between here and Mars. Now, this epoch of space vehicle exploration and discovery reminds me very much of the epoch of sailing ship exploration and discovery, beginning in the late 15th century, a tradition which England played a noble role in. Here is a galleon of the sort that was used to explore what was then called the New World, and what we now call the Americas, but there are lots of truly new worlds awaiting exploration. The benefits of this sort of exploration, I think, are many. First off, there are practical advantages. We are stuck on the Earth. There are many sciences having to do with weather, climate, geology, and biology whose perspectives are profoundly limited by the fact that we only have had a single example to study. When we look at other planets, the powers of these formerly earthbound sciences are tremendously increased. I believe the entire cost of unmanned planetary exploration, which is very inexpensive compared, say, to defense budgets, is returned many times over by the ultimate practical advantages. In addition, we probe the deepest questions. We ask about the origins of worlds and life. We explore our surroundings in space. Every human civilization has asked questions about what is up there. Now, for the first time, we have a chance to find out. And finally, human beings are a curious, inquisitive, exploratory species. I think that has been the secret of our success as a species. We now have reached a point in human history when all the Earth is explored. There are no new places to explore on the Earth, with the possible exception of the ocean bottoms. At just this moment, these spacecraft permit us, in a halting, tentative, preliminary way, to leave the Earth and examine our surroundings in space, an enterprise which I believe is in the truest human tradition of exploration and discovery. We are, as I said, at an epochal moment. Our machines, and eventually ourselves, are going out into space. I believe that the history of our species will never again be the same. We have committed ourselves to space, and I do not think we are about to turn back. I believe the time will come when most human cultures will be engaged in an activity which we might describe as a dandelion going to seed. Artifacts from Earth are spinning out into the cosmos, and human beings will never again be restricted to this one planet.